Hey, this is Pranav Marneni with Lab 5 Magnetic Braking with Faraday's Law. So for the introduction, the purpose is to observe and collect data from a magnet falling through a conductive tube of aluminum foil in order to demonstrate Faraday's Law. And here for the fundamental principles, we use Faraday's Law. Seen here, we use Lenz's Law. We use the Biot-Savart Law. We use Newton's laws and the time derivative of the magnetic flux as seen in this slide here. And then for the preview, we noted that the experimental results of this was that it took 1.236 seconds for the magnet to fall through. And then based on the model, we found out to be 1.188 seconds. We'll get into this more later. So for the model and assumptions, our model to act as a magnetic dipole, a bar magnet was used while the aluminum foil passed through modeled a tube through which it fell. And we assume that the bar magnet can act as a dipole, that air resistance is negligible, and that gravity and magnetic force is the only thing acting on this magnet. So if the experiment, the system was the aluminum tube and the bar magnet, while the surroundings were everything else. As far as the setup of the experiment, using the magnometer on my phone, I identified and marked the north pole of the magnet. Next, I set up a camera to record and drop the magnet through the aluminum tube 5 times. Finally, I analyzed the video footage to determine the time it took for the magnet to fall through the tube during each of the 5 trails. And you can see like a little model right here on the side. Here we have the dimensions of the foil as well as the dimensions of the bar magnet. We also have the time taken to pass through the tube and all these different trails and the average here. Then for the checkpoint of why we can't use a ferrous tube, so basically these type of tubes have magnetic properties which would have interfered with the results of the experiment due to the magnetic fields. And then as far as the magnet, comparing it to falling in free space in a tube, it would fall slower in the tube due to the magnetic force acting on it, which is caused by the induced current of the magnetic field going through the foil, as shown by Faraday's law. Here for the glow script, we set our physical constraints, we set up our graph and all these parameters for this simulation. Here we initialize the tube through a series of rings as shown here. Then we create a bar magnet. Here we give it a bar mu and a mu hat, which we're gonna use later. Here we also set up the magnetic field of a dipole using the principles shown before. And here you have the d flux over dt, the derivative for that for Faraday's laws calculation here. And then here we have a simulation group to show the bar magnet falling through the tube shown here. We'll get into what the red and the blue mean in this next slide or the slide after that. And here we also have a velocity meters per second here. You can notice it's pretty unstable. Then it like evens out after a while. And then we see the time would be 1.188 according to the model. Now the intensity of the color on the tube indicates the magnitude of current flowing in each ring. We find that the red is the counterclockwise direction and the blue is the clockwise direction due to Lenz's law. And as far as like flipping the magnet around, nothing significant would have happened. Only the direction of the currents would flip in our model. And then as far as comparing the time between the model and real life, they're actually quite similar. The tiny differences could have been due to not taking into account drag or the inconsistencies in the aluminum foil. And then, as discussed before, the shape of the graph tells us that at first the forces aren't balanced, and then they eventually even out. Now for our discussion, as far as errors goes, there could have been some discrepancies from not taking drag into account. There could have obviously been some imperfections in the aluminum foil. It's not perfect. And there were going to be errors in accuracy and measurement. Now, the resistivity of the conductor was reduced as close as possible to zero. There would be a lower resistivity, meaning that a larger induced current could have occurred and this would mean that the falling magnet was opposed more effectively. Now, if there were holes cut into the tube, basically this would mean that the current was not effectively going to flow because current needs a continuous conductor. So basically this would make opposing the falling magnet harder and the falling magnet would have dropped a lot quicker.